Hello and welcome back to our last week of classes. We have 3 lessons left and then we are done. Holy smokes, can't believe it. Today and tomorrow, so Monday, Tuesday, are bigger lessons. There's quite a bit of content, and then Wednesday is tiny, and then we're wrapping things up. So if you're on schedule and working hard, you will be done Chem 30 this week. Yay. That's exciting news. Okay, so we're going to dig into this right away, and we are on page 330 in your study guide if you're following along and filling in your notes. And we're going to be looking at a couple things today. We're going to go into detail on pH curves and understanding the sort of shape and the different areas of a pH curve. And you did this in Chem 20, maybe not quite to this level, but this is a review for you. And then after that, we're going to talk about acid-base indicators, and you touched on this in Chem 20 as well, but again, we're going to do a little more detail in Chem 30. So these are topics that if you did well in Chem 20, then that pays dividends for today and tomorrow, where we review that and do some extra. Okay, so we're going to look at pH curves first. So we've got this example of a pH curve. First question. So I'm just going to go through these questions and explain things as we go. Why is the pH constant in the buffering region? So here's our buffering region. It starts at the beginning of the titration and ends right at the edge of the shoulder. We call this the shoulder of the pH curve. Guess I could label that on there. Shoulder. Okay. So why is the pH pretty constant? It started at about 13.5 and it's finishing at 12. So during that time, we've added a large volume of acid, about 23 mils. And the acid is HCl, or H3O plus for a strong acid. So we've added a fairly large volume of acid and the pH has hardly dropped. Why? So every time we add a mole of H3O plus, strong acid, the pH should drop. But it is immediately reacting with the hydroxide that's present. We are starting off with 25 milliliters of NaOH, which is a strong base. And that's why our pH is 13.5. So we have 25 milliliters of this, and we're adding this drop by drop. Every time we add a drop, it is immediately neutralized into water. So we end up with water, and we still have strong base left over. Our pH stays high. Okay, why does the pH drop sharply at 24 mil? So at our shoulder, why does the pH suddenly drop? So we're still adding H3O plus to the OH minus, but at the shoulder, there are only a few drops left. So we're making water again, but there's almost no hydroxide to neutralize. So now the H3O plus can remain. And if there's H3O plus around, our pH plummets because now we have a strong acid in water. So from here to here, from our shoulder to the end, is literally 2 to 3 drops to get from there to there. It could go that quickly as we've used up those last molecules of hydroxide. Okay. Why is the equivalence point at a pH of 7 for this titration? So let's talk about the equivalence point. The equivalence point is where the moles of acid equal the moles of base. So that's where the equi comes in, equivalence, equal moles of acid and base. So in other words, we've added, let's just make up a number and say 2 moles of acid to exactly 2 moles of our base, giving us water. And if this was balanced, it would be 4 moles of water. And water has a pH of 7. So when you titrate a strong acid plus a strong base, you always get a pH of 7 when the acid has neutralized the base, the equivalence point. The equivalence point physically is also the same spot as the endpoint. So it has two names, and the endpoint is where we see a property change, usually color because of an indicator. So the P in endpoint stands for property change. And as it says here, they are the same point. Two names for the same spot. I know, weird. It's like that darn valve in biology, the mitral, bicuspid, semilunar. Three names for the same valve in your heart. It's ridiculous. I hate it. Okay. By the way, did you know I have three first names? That's a little bit of trivia for you. Try and figure that out. Brian is one of my three names, along with the last name. Okay, what are we looking for? In your textbook, they call this section a buffering region. That's a mistake. It is not. Okay, it's not a buffering region. Okay, Bronsted-Lowry reaction that's going on here. We've already done it. It's a strong acid. So if some of you guys were writing HCl like this, it's not. It's H3O plus and Cl minus, and that's the strong acid that we're after. The NaOH dissociates, and it's the OH minus that we're after. So this is the Bronsted-Lowry reaction. Strong acid or strong base, as long as either one of those is strong, this thing is greater than 99% or quantitative using the 5-step method. Okay, we don't need to answer that question. All right, so let's roll on. That's your introduction to pH curves. So you need to be able to pick an indicator that will show you the equivalence point, and it changes color at the end point. Which of these three indicators is best suited to show the equivalence point? Alizarin yellow, bromothymol blue, or orange 4? And your answer would obviously be bromothymol blue. If you used alizarin yellow, you would stop too early. You would be before the equivalence point. And if you used orange 4, you would stop too late. You would have missed it. So in theory, bromothymol blue, it starts off blue, even though I wrote that in red, and it switches to yellow. So if you nailed this one, Roy G. Biv, start with blue and go to yellow, you may actually hit the green right at the equivalence point, which would be impressive. As you transition from blue to yellow, if you can catch this in that intermediate color of green, you have nailed it for this particular indicator. HBB, BB minus, then there's BB8. Oh, different story. So this is the acidic form and this is the basic form. Those are the two ways we could write bromothymol blue. We'll talk about that more later. At what volume would you stop this titration? Well, if we read down, it looks like about 24 mil. And our pH is 7. That's because we have a strong acid reacting with a strong base. Okay, and what other indicators would be suitable to use from your data book? I'm not going to worry about that. Okay, so bromothymol blue is a good one because it changes at a pH of 7. So in our data book, if we look at the indicators, I got to flip this around. What other ones switch at around 7? So there's bromothymol blue, 6 to 7.6. Here's another good one, phenol red, 6.6 to 8. That would be your next best choice, phenol red. And I'm just going to go sneak a peek at that one again. So phenol red, 6.6 yellow, and 8 red. So on this curve, if we used phenol red at 8, it would start right here, red, and at 6.6, it would be done at yellow. So that one would also shift color. And again, if you nailed that, you'd hit the orange, red to yellow, and intermediate color of orange. So that would be a very good indicator to show this equivalence point as well. How do indicators work? Well, that's what we're going to look at next. Okay, so you've got a list of indicators in your data book. It is a table of relative strengths, and it is in order. This is the strongest acid. Wow, these things are acids? Yes, they are. They have Ka values. So methyl violet is the strongest, and then cresol red, thymol blue, orange 4. We can keep going down. They're getting weaker, these acids. Oh, there's HBB that I told you about. Getting weaker, getting weaker. Here's our weakest acid. But it has a conjugate base. And guess what? If that's the weakest acid, then it is the strongest conjugate base. Crazy. Yes, so it's like a table of relative strengths. Here's all our bases. Here's all the acids. The acids get weaker and the bases get stronger, and opposite going up. So if this is our strongest acid, this is our weakest base. And they always come in pairs. And they have Ka values, but we could also calculate the Kb value of the conjugate base. We don't have to, but you could. And they give you the pH range and they give you the color ranges. You had a little bit of this chart in Chem 20, you just didn't have the Ka values. You would not have understood them at the time. Whoops, okay. Let's jump back. Where are we going here? Okay, so past this table, we'll use that later. How do acid-base indicators work? I know you're going to think I'm a huge nerd, but I really find this interesting. So an indicator is a weak acid, weak base conjugate pair. Okay, they always come in pairs. And the pair has two different colors, an acidic form and a basic form. Okay, we write them generically as acidic, H, indicator, and basic, In minus. So the only difference between those is an H plus. And remember that every conjugate pair differs by an H plus. So using Bronsted-Lowry theory, we can show how general indicators work. So we're going to say that HIN is red and that In minus is blue, our acidic form and our basic form. So red and blue with intermediate colors. Okay, in an acidic solution, acidic, so we're going to say it's a strong acid, H3O plus. Which of the indicator pair would react? The acidic red or the basic blue? So Bronsted-Lowry says our strongest acid will go after our strongest base, which would be the basic form, which is blue. The acid donates a proton to the base. Acid becomes water. And the In minus becomes HIN, or its red form. So this one is switching color from blue to red as the strong acid attacks the weak base form. And in the middle of this would be our intermediate color of violet. So if we stop this halfway through, so we've used up half of the blue and turned half of it into red, we would get that violet from that mixture of the two colors. Okay, so you're starting to see the pattern. In a basic solution, the strong base will go after which of the two indicator pair, which pair of the indicator, which of the pair, the acidic or basic? Well, the strong base will attack the strongest acid, the red form, and turn it into its blue form, and will have water left over because it is gaining the proton. Bronsted-Lowry theory, okay? Red switches to blue, violet in the middle if you have a mixture of the two colors. So that's the basic idea behind acid-base indicators. They're weak acids, weak bases, and they have colors. So we're going to zoom in on one of these just to take a look at it. Okay. So this is methyl red, and methyl red has an acidic form and a basic form. Its acidic form is red, and its basic form is yellow. There's its pH range, and there's its Ka value. So it's one of the stronger weak acids, one of the stronger, more acidic indicators. And here's the actual molecule. So I'm going to zoom in on this thing. This is a pretty complicated organic compound that has two benzene rings. There they are. A nitrogen to nitrogen double bond, a nitrogen with methyl groups. Anyway, it's a big complex molecule. Here's the key part. Here's the acidic form, COOH, and here's the basic form, COO minus. The only difference between these two giant molecules is that one region. And it's crazy that missing that single H plus changes the shape of the molecule so that it will reflect yellow light. So when your eyes look at that molecule, yellow light is coming off of it. And when your eyes look at this molecule, red light is coming off of it. And it's just due to that single proton, which is, I think, amazing. So that's the difference between indicators structurally, a single proton. And it says here that a base will start pulling the H plus off at a pH of 4.8. So it's in its acidic form. And then at 4.8 or higher, it starts to switch to its basic form as it loses protons. Okay, so that's the idea behind that indicator. And if you're stuck in the middle, you've got a mixture of both. You have orange as its intermediate color. Okay, how would you classify methyl red as an acid? Strong or weak? All of the indicators are weak. There are no strong ones. What acids are stronger, or what acid is HMR stronger than? Sorry, what acid is HMR stronger than? How could you figure that out? Well, we can go to our acid table of relative strengths. I'm just going to go back here. This is important now. Its Ka is 1 times 10 to the minus 5. So let's go look at our acids. One times 10 to the minus 5. Okay, where is it? 1 times 10 to the minus 5. Okay, so here's our acids. Zoom in a little bit. There's 6.3 times 10 to the minus 5, 1.7, 1.5, 1.3. So it would sit right below that. Okay, so that means propanoic acid is stronger, carbonic acid is weaker. So it would sit right between these two acids, right below propanoic acid. So it's stronger than carbonic, it's stronger than hydrogen citrate, it's stronger than hydrosulfuric, it's stronger than all of these. So you can use that Ka value to compare the relative strengths of indicators to other acids. Stronger than H2CO3 and all acids below it. On table of relative strengths. Which indicators are the strongest acids and which ones are the strongest bases? Okay, so I think we did this already. Just flip that around. Yes, we did. So these are our strongest acids. And way down here are our strongest bases. 1,3,5 trinitrobenzene basic form, indigo carmine basic form, alizarin yellow basic form. Hey, little trick for you. If you ever want to figure out the pH, you take the negative of the Ka value. This one's negative 13, which means as a base, its pH is about 13. IC minus is negative 12, so as a base, it's about a pH of 12. And you can see what happens as we move up. These things get closer to neutral when you have both of those, and then the acidic one dominates. So our strongest acid, HMV, has a pH of about 1, which is pretty strong. And Crescel Red has a pH of 1 as well, and it's most acidic. So those are fairly strong weak acids. You can do that same thing actually with these guys as well. I never told you that, but you can. Flip this one around. So if I want to know the approximate pH of benzoic acid, it's about 5. And butanoic acid is about 5. And if we go down to our strongest bases, PO4 minus is pH of about 13. And if we go up to our strongest acids, oxalic acid is a pH of about 2. So those Ka values are kind of useful for quick estimates of pH as well. Okay. Notice their pH ranges correspond to their Ka values. So you take the negative of the exponent of the Ka to get the approximate pH. Wow, I know. So exciting. You probably want to stop this video and run and tell your mom or dad what you just learned. I don't blame you. I would too. If you add alizarin yellow to an acidic solution, what color will the indicator become? So if we add it to an acidic solution, the H3O plus will go after the basic. And alizarin yellow is, just gotta look that one up here. It sucks that I have to keep flipping this thing around. Alizarin yellow. Did I miss it? Was I not paying attention to it? Oh, it's way down there. Okay, alizarin yellow. So switches yellow, acidic, red, basic. So yellow, acidic, red, basic switches to its yellow acidic form as it becomes acidic or gains the proton from hydronium. Okay. Whew. Half done. So that's acid-base indicators. Now the second half of this lesson is choosing indicators based on Bronsted-Lowry reactions and the table of relative strengths. So you're not given a pH curve. It's a little trickier. This is one of the harder topics. So pay attention. Pause the video. Go get a glass of water. Have a drink of water. Go outside. Breathe some fresh air. Get yourself perked up so you can grab onto this idea. How do you choose an appropriate indicator for an acid-base reaction when you have no pH curve to figure out the equivalence point? Okay, here we go. When choosing an indicator to show pH at an endpoint, you must choose an indicator that changes its form after the last quantitative reaction. This will ensure that the indicator does not react until after the equivalence point has been reached. So the trick is you always choose an indicator whose Ka makes it weaker than the species that you're trying to titrate. That way the indicator is only converted to its conjugate partner after the acid or base has been used up and truly shows the equivalence point has been reached. Now that's pretty theoretical. You may be thinking, what the heck does that mean? So I will show you that. Okay, and I've got our table of relative strengths right here. Okay, so I've put the two tables side by side. So here's our acid base and here's our indicator, table of relative strengths. Okay, so let's pretend that I am titrating a strong acid with this base. Okay, strong acid with that base. When I am done and I've used up all of this base, I want the solution to change color. So I want my strong acid to then change the color of an indicator. So would I pick an indicator that sits in A or in B? If you chose A, then the strong acid would attack A first because it's a stronger base. B is a weaker. I got that one backwards, my bad. It would attack, I can't believe I did that. Cross out that W, it would attack B first because B is a stronger base. And we don't want that. We want it to use up the SO4 2- first, and then we want it to go to the weaker base, which is sitting in position A. So how do we figure that out? Okay, well, the strong acid attacks the sulfate. Then we want it to go to the next strongest base. It has to be weaker. So this has a Ka to the -2. So we need an indicator that has a Ka to the -1 would be nice. So we go look on our table and there are two indicators that have a Ka to the -1. 2 times 10 to the -1 and 3 times 10 to the -1. So if I wrote those right in this table, they would sit right here. Cresol red, and methyl violet. They would sit right here. 3 times 10 to the -1 and 2 times 10 to the -1. So strong acid attacks our strongest base, and then it attacks whichever one of those I choose to use. They are very, very weak bases. They're almost as weak as water. Okay, they sit just below water on the base strength. If I chose, let's go with this one, orange 4. It is 1 times 10 to the minus 2. It's the exact same as this. That would muddy the waters. They'd both be changing at the same time. If I chose methyl orange to the negative 4, 3.5 times 10 to the negative 4, it sits right here. 3.5 times 10 to the negative 4, methyl orange. It's too strong. So the acid would attack methyl orange first, and then it would attack SO4 2-, and that would be wrong because our indicator would get used up first. As soon as you added a drop of acid, it would switch the methyl orange from its basic form. Where is it? Methyl orange MO. MO- to its acidic form, HMR. It would change color. One drop, it would change color, and the titration would be done. No good. Okay, now let's flip it around and do the opposite. So now I'm going to add a strong base, hydroxide, to this acid. So this is our titration. We have a strong base, and we have this weak acid. Do I want my indicator to sit in position A or B? So remember, the idea is our strong base should completely use up our acid and then attack the indicator next. So the indicator needs to be weaker than HCN. Is it weaker if it's in position A or B? There's water. So B. We would want an indicator that sits down in this area somewhere. So we use the Ka value of our acid to the negative 10, and we want something with a lower value, negative 11, negative 12. So here's two good choices. Alizarin yellow or indigo carmine would be good choices because they both sit right down in this region. So then in our titration, our strong base would go after the weak acid, and then it would go after the indicator next. So that would be reaction number 1, reaction number 2. So you can see they're opposites from the bottom of the table when you're using a strong base with a weak acid compared to when you're titrating a strong acid with a weak base. Okay, should put W there. That's a weak base, and then we choose an even weaker base as our indicator to go after. So that's the basic idea. Haha, that's a pun, the basic idea. Okay, so let's try this out. What does this look like when we're actually using Bronsted-Lowry theory? Consider a solution of K2CO3. So that's ionic. That dissociates into K plus, CO3 2-. So I'm getting set up to see the reaction. We have phenolphthalein as an indicator, which has an acidic form, HPH, and a basic form. And it's titrated with hydrochloric acid, which is H3O plus and Cl minus, and there's water present. I'm going to not write aqueous just because it's going to get crowded. Okay, so Bronsted-Lowry theory, there's our strongest acid. So we know we're adding H3O plus. We want our strongest base. So it's either CO3 2- or pH minus. Definitely not water. That is the weakest base of them all. So we have to go look it up. CO3 2- or pH minus. CO3 2- is right here. And pH minus is right there. So CO3 is negative 11, and this is to the negative 10. So phenolphthalein would sit right here. pH minus. Okay, decision time. So which one does our strong acid, which sits way up there, which one does it attack first? CO3 2- or pH minus? Well, here's our strongest base. This one is a stronger base, and this one is a weaker base. So CO3 2- goes first. CO3 minus will go first, and then the acid will go after the basic indicator next. Okay, add a proton, HCO3 minus, and water. The titration has not changed color yet. Now it does. pH minus is pink. It switches to its acidic colorless form, and water. And as soon as it switches, you would stop. And that's why you only add a few drops of indicator so that they are used up very quickly when you add that strong acid. A few drops of acid will use up all the indicator and switch its color from pink to colorless, and then you would stop and you know that you have used up all of the base. Quantitative 100%. Used up all of it. So that's how you pick an indicator. It's all about comparing Ka values. This one was to the -10, and this one was a weaker base to the -11. Okay. Let you look at that for a second. We're going to do 2 more examples and then we're done. Whew, heavy day. I would say this is probably one of the biggest topics in Chem 30. I know when I teach this lesson, I teach the entire period. The students don't get a break. It's a grind. K plus, HSO3 minus, phenolphthalein, HPH, pH minus, nitric acid is a strong acid, and water. Okay, these are all the players. That's obviously our strongest acid. We're going to be adding H3O plus. Write the list of species present. Done. Show all the reactions that occur in their correct order. Okay, so strongest acid will go after the strongest base. So this is a weak base. Anything with a minus is a weak base. Super weak base. It's weaker than water. Weak base. Okay, so I think the issue is between these two. Well, I know it is. HSO3 minus or pH minus. Which one is stronger? HSO3 minus or pH minus? Whoops, I don't need that. HSO3 minus or pH minus. This is a mess. Okay, I'm going to make all this disappear. HSO3 minus or pH minus. Okay, so we're using our strong base. So we'll keep that guy. Let's switch colors. So, we're titrating with strong acid. Go up to our strong acid. So H3O plus, and we have HSO3 minus. Let's clean this up a little bit. Okay, that's enough so you see what's going on. Okay, so strong acid can react with HSO3 minus, and phenolphthalein is to the -10, which is way down here to the -10. It's off of this slide, sits way down here. So we'll just, for simplicity's sake, let's put it down here. pH minus times 10 to the -10. Okay, so who is this strong acid going to go after first? Here's our 2 players. Strong acid goes after the pH minus first. It's a much stronger base, and then it will go after the HSO3 minus. So pH minus is a stronger base. Then once it's used up, then it goes after the next strongest base. So you should be looking at this going, oh, okay, this is not good. That means our indicator is used up first. So a few drops. So as soon as you add a few drops of acid, the color changes from pink to colorless, and you stop. And you're like, everyone's hand goes up, and you're all calling me over in the lab and going, Mr. Johnson, it changed color after I added 2 drops. How come? I'm going to go, crap, we chose the wrong indicator. This indicator is a stronger base than the base we're actually trying to titrate, and the indicator went first. So that's a dud. you'll never actually get to this step of switching it from its base to its acid because you stopped due to the color change. So really, we needed an indicator that was down here, a weaker base. Weaker basic indicator needed. So I show you this example just so you realize they don't always work out. You got to pay attention to those Ka values and make sure you get it right. Whew. Okay, last one. This one's a bit of a beast. Challenge question. When I converted this to a PDF, it was not very friendly. It put all these weird spaces in. Okay, I don't know if I left enough space for this guy. A student titrates a solution of C3H5O COOH 3. It's called a triprotic acid. It has 3 carboxylic acids that it can donate. There's bromothymol blue, HBB, BB minus, being titrated with a strong base, Na plus, OH minus, and water. Okay, so our strong base is the hydroxide. This is a weak acid, so it stays together. Here's a weak acid and a weak base. So we're adding OH minus. So the question is, who does OH minus go after first? HBB as a weak acid or this one as a weak acid? So we got to go look it up. Okay, C3H5COOH and BB, HBB. So back to our messy tables. Okay, so bromothymol blue is to the -4. Bromothymol blue is -4. So that means it's up here. Bromothymol blue is 5 to the -4. So it would sit right here. Let's clear this one out. Should have had a bunch of these tables ready to go because this is a bit of a mess. It's okay. Chance for you to take a little mental break as we dig into this last one. Okay. 5.0 times 10 to the -4. I always write these right in the table. BB minus HBB. So now I can compare it to all the acids. Okay, so we're using hydroxide, which is a strong base. So we're titrating with this guy. So we want it to attack our acid first and then our indicator next. So we're choosing the strongest acid and hopefully the indicator is weaker. So where is it? C3H5COOH. I got this backwards. Did it again to myself. Gosh. This will be the weaker acid. This will be our indicator sitting here. Oh my gosh. Monday morning. Okay, so weak acid, strong acid. So they get stronger as we go up. So let's go searching. Bromothymol blue. I've written it in. It's way up here. Bromothymol blue. It's right there to the -4. Okay, so there it is as an acid. Did I do that one right? I don't think I got the number right. Bromothymol blue. Okay, I need reading glasses. It's to the -8. Oh my gosh. This is called a comedy of errors for Mr. Johnson. To the -8. That's why things weren't quite sitting right in my head. So we got to jump back down to this one and put it in its proper spot. 5 times 10 to the -8 would sit right here. See how hard this topic is? Your teacher is messing it up. Okay. BB minus HBB. Let's get rid of all this stuff. Okay, so here we go. Our strong base picks the strongest acid. There's HBB, and we're looking to compare it to C3H5COOH, which is actually quite strong. It's way up here. Here it is. So that is a much stronger acid than bromothymol blue. And interestingly, this one has a couple other forms as well. So it donates its first proton and becomes another weak acid, which is this guy, which is crazy. That's why this is a challenge question. So it has a second form, which is also a weak acid. Here's the product, which is also a weak acid. This is unbelievable. So this thing has 3 weak acids. And then finally, we get down to the weakest acid of them all, the bromothymol blue. So our strong base goes after that really strong one up there, and then the next strongest, and then the next strongest, and finally gets down to bromothymol blue. Whew. So what does all that look like? Okay, we can remember that to fill this one in. So the strong base goes after this one first and removes one of those protons. So we are left with C3H5O, COOH2, and we've removed one of them, and water. What a mess. Okay, now this guy is also a weak acid, so it can react again. Do you see why this is a challenge question? That should be C3H5. C3H5O, COOH2, COO minus will then react with the base, and this proton gets transferred. So now we're at C3H5O, COOH, COO minus. Now we have 2 of these, and water. Right now you guys are ready to puke, aren't you? Last weakest acid, C3H5O, COOH, COO minus 2, plus hydroxide gives us C3H5O, COO minus 3, and water. And finally, the indicator can react after these 3 weak acids are done. And the indicator was HBB. HBB reacts with the strong base to give BB minus and water, and that would be your color change. This one is yellow, and this one is blue. I would not ask you to do one of those, maybe on an assignment when you have this example, but that is a beast. That is a challenge question. What a nice way to start our last week of Chem 30. You will find these much easier. So to practice this in your textbook, page 754, numbers 1 to 4, and that's it. And the answers are all here. So after you've done them, you can come back and check on the video. Okay, there's 1, and 2, 3, 4. Okay, so you can pause and check them. All right, I know that was heavy. I don't even want to look at the time when I stopped this thing. It was a long one. Tomorrow, not so bad, and Wednesday, super short, and then we're done. So nothing but good news from this point on. Okay, take care, everybody. We'll see you guys tomorrow.